The last special random variable, as the book will talk about, it happens so often that we gave it a special name, a geometric setting. We looked at a binomial setting, right, where probability of success was the same each time. There was a fixed number of trials. They were independent. And what was the fourth one? You guys tell me. All right. A geometric setting arises when? What makes something geometric? The big thing about geometric is that the variable in question is the number of trials until the first success occurs. So geometric means we're going to do it until we get the first success and then we stop. Binomial, we did it a fixed number of times and tried to find the probability that a certain amount would be successes. Geometric, we do it until we find the first success. So what makes something geometric? What makes something the geometric distribution? Well, only two things can happen. For simplistic reasons, let's say success or failure. Each trial is independent. Hey, we've seen those two before. Those were the same rules for binomial. Only two things can happen. Each trial is independent. The probability of success is the same for each trial. Wait a minute, Mr. Claycamp, you're screwing up, man. That's the same rules we use for binomial. No, geometric and binomial, the first three are the same. The only difference is the fourth one, okay? In binomial, we said there are a fixed number of trials. In geometric, the variable of interest, what are we looking for? Is when the first success occurs. Okay, so the variable of interest is the first success. When do we find the first success? So binomial and geometric, three of the four to find the binomial setting or the geometric setting are exactly the same. Only two things can happen, success or fail. Each trial is independent of the previous trial. The probability of success is the same every time. Now for geometric, the variable of interest is when do we find the first success? In binomial, it was a fixed number of trials. So this is the only one that makes geometric different from binomial. Let's take a look at geometric. Okay? There's a couple of formulas for geometric. Okay? So if I want to know what is the probability that my first girl is the third girl? Well, it's pretty simple if you think about it. Remember what we said before, the probability of a girl is equal to 0.75. Well, if the first girl happens, let's say, on the third child, what's the probability that my first girl happens on the third kid? Well, that means that what happened on the first kid? Oh, I had a failure. Sorry, boys. I failed. The second kid, I failed again. I had a boy. The third kid, I finally had a success or a girl. Right? You guys all would have been able to answer this question without seeing any formulas or me telling you anything. Makes sense. The first girl I have is on my third child. That means my first two children were boys. Okay. Well, what's the formula look like? It says you take the probability of a failure, which is 1 minus p, raised to the number of failures you want, which in this case is one less than the number of that I want. If I want my first kid on my third one, that means I have 2 failures times the probability of success. Simple formula, very simplistic, easy to use, makes total sense. The calculator can also do this for us. Well, let's look at our favorite strong friend here, the one that does all the heavy lifting for us. And let's do this. Let's take 0.25 squared times 0.75. Oh, okay, 0.0468. The probability my first girl is on my third child is about 4.6%. assuming all the other things are true. Like we said, the probability of a girl is 0.75 and so on. Okay. Now, we can also do this on the calculator. We can use something called the geometric PDF. Okay. Geometric PDF. Wonder where we find this at. Okay. Geometric is a type of distribution. Where do we find distribution? Believe it or not, in the distribution menu. Okay. Geometric PDF. GPDF. P. What's the probability of success? Oh, 0.75. X. When do I want the answer to occur? Oh, on the third kid. Paste. Enter. Oh, 0.046875. Imagine that. It's the same answer we found. Okay. Now, again, if you don't have the 84 or above, you'll have to go to the geometric PDF the same way we do, but then you'll have to do parentheses 0.75, comma 3. All right, so geometric is probably easier formula-wise, certainly by hand, than the binomial. Calculator, it's all the same, right? Because we're not doing any of the work. So as long as we understand what we're doing, it's pretty easy. How do we find the expected or the mean number of children before the first girl occurs? So what is the center of a geometric distribution? Okay. The mean or the expected. Remember, anytime we see the word expected, it tells us mean. We need to make that connection immediately. It's just 1 over P. So how many girls would we expect to have? How many children would we expect to have until our first girl occurs? Well, we would just take 1 divided by 0.75. Okay. So we would expect to have how many? Can we do 1 divided by 0.75 in our head? We don't have to. We got the strong guy to do the work for us. 1 divided by 0.75. Well, I'd expect to have 1 1/3 girls until my first girl occurs. Again, it's okay for the mean and standard deviation to not be a whole number. So the formula is pretty easy. Okay. Probability that x equals k is 1 minus p to the k minus 1 times p. It doesn't sound very simple, but when you think about it, you all could have answered this question and probably did in your head before I even started talking and showing you any of this work. We can also do geometric PDF, geometric CDF. Whoa, what the heck does that mean? Geometric CDF? What are you talking about? Well, let's clear this page out and let's look at an example. There we go. So let's say, remember again, the probability of a girl is 0.75. And n equals 5 means we're going to have 5 kids. Okay. This n only applies if it's binomial. So for this geometric, we don't know how many kids we're going to have because the geometric variable of interest is the number of trials until the first success is attained. Okay. So I want to know what's the probability that my first girl happens on my third child. Well, we just did that. We said that that was geometric PDF, and we had to type in, was it NP or PN? What did we put in? Oh, look, the P comes first and the N comes second. Okay, so it's PN. How is this different from binomial? There's no n, so we just drop the n at the end. Okay. Other than that, it's the same. What if I want to know that I have my first girl by my third child? Oh, this looks very similar to what we saw in binomial. This is a CDF problem. So geometric CDF up to what I want. What if I want to know the question, what if it takes more than 3 children before I have my first girl? So what's the probability that x is greater than or equal to 3? Just as in binomial, when I want greater than, CDF only counts from the beginning up to what I want. And in this case, a 0 makes no sense for geometric because I can't have my first girl on my 0th child, right? I can't have a girl until I have a kid. So 0 doesn't exist in geometric like it does in binomial. So if I want the probability that it takes at least 3 kids to have a girl, my first girl, I'm going to have at least 3 before the first girl occurs using the same language we used before. I'm going to do a CDF, but I want a 1 minus geometric CDF. So I'm going to subtract everything I don't want, and that will leave me with what I do want. Okay, so that would be how I would do it. So let's put this in a formula for us. The probability that X equals K or N, either way. So that's geometric PDF of P, comma, K. What if I want to do the probability that X is greater than or equal to K? That's geometric CDF PK. You can think of K as X or whatever you want for geometric. Now, what if I want to know the probability that X is greater than or equal to, I want to know the probability that X is greater than or equal to K. Then it's 1 minus geometric CDF of P, comma, K minus 1. So I know that was a whole bunch, guys, but we made it. We're done with chapter 6 and all the different types of random variables. And I'm as happy as you guys are.